Okay, let's begin. Welcome back, everybody. So we're going to finish this Poisson predictive problem. We just have a couple steps to do. Did anybody go and look up the expectation and the variance for the negative binomial in the parameterization that I wrote down? What was the parameterization? Yeah, nobody ever does. And it's okay, I'm never going to quiz you on it. So if it comes up, it'll come through one of these mixture representations, and you can use the iterated forms to get it. As a stat student that wants to teach probability one of these days, you should probably go and see if you can do all those things and all the different ways you can do it. It makes you better. So it also invents problems for yourself by doing it a different way. Using maybe the geometric representation, or taking sums of geometrics or something like that. Anyway, we'll go through it. So my expectation is that you guys do not know that off the top of your head. So most people don't, but it's definitely worth being able to recognize things quickly. So the representation that we were looking at for the negative binomial, its equivalent up to a shift is the other common representation where you count the total number of trials, including the number of failures. But this looks like this. N minus 1, choose R minus 1, P to the R, 1 minus P to the N minus R. So it almost looks just like a binomial distribution, except the random variables are in different locations. And the normalizing constant is a little bit different. So this is the number of successes. And usually in a binomial, that's the random thing. The number of successes that you're going to get out of n fixed trials. So this is going to be fixed in this model. This is the number of trials. You wanted to model just the failures being the random thing. That's the other parameterization of this. This is the sum of geometrics. So a geometric distribution is the expected waiting time by flipping a coin with probability p until you see your first success. So if R was 1, this is a geometric distribution. You probably work through just intuitively what the expected waiting time is for that. It's 1 over p. So if on average you see a success a tenth of the time, how often would you need to flip the coin to see one success? Probably around 10 times. So you can also quiz yourself just on the intuition of everything as well. I just feel like once I start oh, it's all very intuitive, and I can make all these connections, that's when I kind of get it. That's the negative binomial distribution. So this is the random thing. I'll just point out, in terms of the likelihood function, that's defined right here, if this was a function over p, it has the exact same likelihood function as a binomial distribution. And so if you just saw a bunch of coin flips, and you didn't know if it was a negative binomial experiment or a binomial experiment, you're trying to infer p and you're a likelihoodist or a well-trained Bayesian, it wouldn't make any difference. If you're playing the p-value game, make a big difference. So take an inference class and I'll walk through that. It's the typical example in the likelihood principle. We will talk about that eventually, but we won't dwell on it. Okay, so that's a negative binomial distribution, and a Poisson distribution looks like this. So this is the probability of xi's given lambda is equal to e to the minus lambda, lambda to the xi over xi factorial. The xi's are counts. So those are numbers that live between, on the counting numbers. And this parameter, this rate representation of everything, this lives between 0 and infinity. I guess technically you could let that be a 0, But that would really just be a point mass at 0 if lambda were 0. So you'd always just be counting the same 0 things that never happen. So it wouldn't be a very interesting distribution. Mixing that distribution of point mass at 0 with a Poisson is a very common thing. So we will be studying mixture models in this class, and we'll see another one today. Any questions about all that? So we know what this stuff is at least. Okay, so the idea is that we're going to get a whole bunch of samples. I'm going to get these whole bunch of x's, and they're going to be these counts. So I'll get n of them. They all come from a Poisson distribution. I probably have already switched my notation. Probability, I think I used F last time, so if you want to interchange that, we can do that. We'll just write F. So, it doesn't really matter. You just need to distinguish whether or not that's a mass function or if it's a continuous thing. It does make a little bit of difference, i.e. calculus. Okay, so what we want to do is we want to forecast. So this is a future point. This is our future, and we want to condition it on x, right here. How do we do that? We take our sampling distribution. If I knew what lambda was, I would just stick that thing in, and I would have the inherent variability of a Poisson distribution. And that would model my inherent variability for the future. We, of course, never get to know this, or at least usually not. And so we're going to estimate it, or we're going to average over our uncertainty given the data at hand. We'll integrate lambda over the entire range of values it can take on. So that's a posterior predictive distribution. Let's just fill this in. Give myself a little bit more space. Later in this lecture, we'll cover MAPs, maximum A-Posteriori estimates, talk a little bit about those, and the Bayesian intervals, the credible intervals. We'll spend a day or so on that. Okay, so our integral looks like this. Integral, we've got our Poisson distribution, so that will look like e to the minus lambda. Lambda to the x tilde over x tilde factorial. So I'll just keep everything written down. We, of course, can't throw that away right there. That has something to do with the random variable. We can't throw away anything that deals with any lambdas. So all this stuff is important. So then we're going to have our posterior distribution. What did we say that was? Let's just work it through real quickly. So we'll just drop that thing down and then close this and solve the integral. So pi lambda, given x, we know everything came from a Poisson distribution. So I know what the likelihood function is. I goes from 1 to n, e to the minus lambda, lambda to the xi's over the xi factorials. Normally I would toss this thing right here and just get rid of it. It scares me just to look at it. So that's because if I try to implement something with that plugged in, that factorial, and there wasn't something in a ratio where most of the stuff canceled, that thing, if you've ever computed a factorial on a computer, you know what a headache it is. So if you've ever computed factorials on a computer and it wasn't a headache, it was because you're taking factorials of things like 30. So in double precision, you'll blow out your computer's memory with what that number is at about 52, 53, something like that. And then people use things like Stirling approximations. So I'm a Bayesian computationalist, so when I see anything in the formula that it's like, oh, I better be concerned about that, I do think about it. We'll leave it in there though, just because we're doing algebra. The nice thing is that it's always just kind of part of something that comes in a ratio. And so you can make this thing stable. Okay, so that's our likelihood function. And now we just need our prior distribution. So probably the gamma. I think I will just not dwell on this and just get rid of it so we can recognize which gamma it is. And then I'll write down everything in its full-blown detail up here. So we'll just do this algebraic step just to recognize which gamma we're playing around with. So e to the minus beta lambda. So that's going to be e to the minus lambda n plus beta. I'll combine those terms. And then I have lambda to the sum of the xi's plus alpha minus 1. And so we know which one this is. This is going to be a gamma. N plus b sum of the xi's plus alpha. So that's what that thing is. So we'll integrate against that. Let me give myself a little bit more room. So this thing right here is going to be the integral. Integrating over 0 to infinity. I didn't write it down there, but I meant to. Yeah?
I think you're correct.
Oh, yeah. I usually do it the other way, too. Sum of the xi's plus alpha n plus beta. Keep it the same way we usually do it here. Okay. So this is going to look like e to the minus lambda. Lambda to the x tilde over x tilde factorial. Then I've got to write in all my other stuff. I know what the kernel looks like. We just wrote that down. That's e to the minus lambda n plus beta, lambda sum of the xi's plus alpha minus 1. And I said I'm going to write it down in its full-blown detail so we can make it look just like that negative binomial thing. So what's the normalizing constant that we usually toss? It's a fraction. I'll do the easy part. This will help you with all kinds of problems in this class. It will definitely come in useful on the midterm.
N plus beta is
Yeah, so what is it in, if I call this thing alpha tilde and that thing beta tilde?
beta is
Yeah, so is it beta tilde to the alpha tilde over gamma alpha tilde? So that's the normalizing constant. Let's write it all down. So this will be n plus beta to the sum of the xi's. Get rid of this box. Sum of the xi's plus alpha. So no minus 1 over there. So over gamma function of sum of the xi's plus alpha. I think most of you know this as well. So the gamma function of some integer, let's say that's an integer, how does that relate to a factorial? Z minus 1. So this thing, this binomial coefficient right here, is n minus 1 factorial divided by r minus 1 factorial divided by the difference between those two things, factorial. So you can kind of see all these factorials popping up in all of this. So there's one of them right there. There's another piece to that puzzle right there. So if alpha was integer, this whole thing would be an integer. And we would have that form. I'm going to write it in a more generalized form and let alpha maybe be something non-integer, but I think of those gamma functions as things like factorials. More realistically, I think of those factorials over there as gamma functions. So I think of more generalized results. Okay. So just keep that in mind. So we can pull some stuff out of this. So let's just simplify everything. Pull things out of the integrand if we can. So this will be n plus beta, sum of the xi's, plus alpha, divided by gamma function, sum of the xi's, plus alpha. I'll suppress some of my notation. This one I'm not going to integrate over, so I'll pull that thing out as well. So I still have these terms right here that I can't remove. And I still have this term right here that I can't remove. So integrate between 0 and infinity, all the rest of the stuff that we can't remove. So let me just soak this term and that term together. So that's e to the minus lambda. This was n plus beta, and there's one of those right there. So I'm going to add this in like that. That makes me actually feel pretty good when I see n plus 1 pop up in a predictive calculation, because I know where that's coming from. So there's variability attributed to n things from our sample, and then there's one more thing that we're forecasting. So very typically, you'll see n plus 1s pop up. Then we're left with the rest of this stuff. Lambda x tilde plus sum of the xi's plus alpha minus 1 d lambda. And I think I know what this integral is. If you were taking a calculus class, you'd start working through parts and starting to think about how to do this, and if that wasn't an integer, what would you do? And if you've been a Bayesian for a while and you know things about likelihood functions and sampling distributions and normalizing constants, you don't even do any math. You just recognize what this thing is. So what is this? So it's gamma of that thing right here. And here's our, our new beta tilde tilde term or something like that. Kind of already used that representation. But we know that this thing is going to be a gamma function of x tilde plus sum of the xi's plus alpha over n plus 1 plus beta to that stuff. X tilde plus sum of the xi's plus alpha. And that's our distribution. And all we have to do is recognize it. So I'm going to get rid of this and just rewrite everything a little bit neater. Going to cheat. Write it down real neatly for you. It's going to look like this. This will look like, so I'm going to do a little bit of simplification here. Gamma x tilde plus sum of the xi's plus alpha. That one's over there somewhere, that's that thing. Divided by gamma sum of the xi's plus alpha. We played with that one before. And x tilde factorial. In essence, that's this. And then there's two other terms. So that will look like n plus b over n plus b plus 1. This is raised to the sum of the xi's plus alpha. And there's one other term. 1 over n plus b plus 1 raised to the x tilde. all I did in doing that is I took this thing right here, that's obviously that, but then I've got this one downstairs that's raised to that thing plus this one. So I factorized this apart in the denominator. There's this many of them here, and then the other one pertaining to x tilde is there. And you'll notice that these things live between 0 and 1, so you could interpret them as probabilities if you wanted to. And lo and behold, I think that looks just like this. So minus the extension to gamma functions and not using factorials. But if you ended up using factorials and everything, you would have those minus ones sitting in here. So if you aren't recognizing the minus ones, it's because of this right there. And that's where those minus ones are coming from. So if alpha was a integer, you could write it exactly like that using a binomial coefficient. So that's negative binomial. And that's what it is. So I kind of like it. We've already talked about it's over dispersed, has more variability than its mean. So it's not as constrained as a Poisson distribution. That kind of makes sense. That if I'm going to try to forecast something, I have more variability than in my original sample. So forecasting always adds variability to something. So that's what this forecast should do. Of course, we haven't written that down. I could ask you, what's the expectation of the variance? And if I asked you something like that on a midterm, you could either spend an hour and a half probably getting it wrong. If you're well trained and you're just coming off of doing QEs and you've done this, you probably do it in 2 or 3 minutes. So, because you already know the trick of how you get something so that it looks like it sums up to 1 and you factorize something out. Maybe you've seen that. Okay, so we're not going to do that. So we want the expectation of x tilde given x, and similarly, we want the variability of that thing. So we'll just apply our iterated forms. Same thing every single time, x tilde given lambda and x. So I'll condition on that lambda, but I'm conditioning everything all the way through on cap x. That's the data that's fixed in the problem when we get to know it. And I think it's useful to write it out with all this notation. So I can figure out what you know. Same thing as always. This is really just a sampling distribution. If I get to know lambda, the data didn't tell us anything. So I can get rid of that. It's conditionally independent given that you know lambda. And so that's a Poisson distribution, x tilde given lambda. That's one of the layers in our hierarchy. That's the sampling distribution. And we know the expectation of a Poisson is lambda. This just looks like this. So that interior expectation, and I didn't write what it's over, but it's obviously over x tilde given lambda and x. All the notations are in there for us. And that's the posterior expectation. And so do we remember what this is? What is it?
Alpha.
So it's alpha tilde over beta tilde. What was that? That was sum of the xi's plus alpha over n plus beta. So we've seen that a couple times, and that's what we worked with when we derived the posterior distribution. So that was our alpha tilde and our beta tilde from our posterior, the other layer in the hierarchy. So hopefully you start to see this integral that we're playing around with. It's really just a hierarchical thing. So that's the posterior mean. So our forecast, just like in the old example, is centered right where the posterior is. That does not always happen. It has to do with what the distribution looks like in the first place, but it's not uncommon for that to happen. Our variance is equally easy. There's just 2 terms in here. Right back here. This is going to be the variance of the expectation, x tilde given lambda x. Everything's conditioned on x, plus the expectation of the variance. X tilde given lambda and x given x. And we can solve each of these pieces. So this is going to be equal to something plus something. So this is going to be the variance of lambda given x. And this is going to be the expectation of the variance. Again, this is conditionally independent. We'd already played with that one, so we knew what it was. We know the variance of a Poisson, it's lambda. So, given x. So this is the posterior variance plus the posterior expectation. That's all you're coming up with. You can kind of figure out when this thing is going to be identical to the posterior thing. It's when you pop the parameter right out there, and it's actually just that parameter for the posterior distribution. That's when the expectations will match. If it's something different, then it's something different. So this is going to be equal to, we'll just write it out the same way. So this thing plus that thing. What's the variance of lambda given x? Yeah, alpha tilde over beta tilde squared. Same alpha and tilde and beta tilde as before. And this one is alpha tilde over beta tilde. So our answer at the end of the day, variance of our prediction is equal to alpha tilde, beta tilde plus alpha tilde over beta tilde squared. We could factorize out an alpha tilde beta tilde if you wanted to. Alpha tilde over beta tilde, 1 plus 1 over beta tilde. So this is representing our additional variability and everything. You can just write that down in terms of the final answer. So this looks like sum of the xi's plus alpha over n plus beta times 1 plus 1 over n plus beta. So if n is big, we notice that this drives down to the original variability of the original distribution. So if n is big, that thing vanishes out. All we're left is the 1 there, and it's the original thing. But this is modeling our additional uncertainty, and it's a function of n. So again, no surprise. We recognize it's a negative binomial by writing it all out, recognizing its kernel, and then we found the expectation of the variance just using the iterative forms. So, could be a hard problem, very easy problem. I also like that if the problem was really hard and we couldn't solve the integrations, if I knew things about those functions in the integrand, I could set up a very easy Monte Carlo scheme. You're going to be playing around with that sort of representation on the future homework. If there were things I didn't know how to sample from, I'd need a more sophisticated Monte Carlo scheme. So most people might run off to Markov chain Monte Carlo. We'll pick up with that next week. So I think this week we'll finish up with intervals and maps, and next week when we come back, we'll start on MCs. Any questions?
Yeah, I'm wondering how you would interpret, like,
I wouldn't.
okay, the x tilde.
Yeah, I wouldn't go back to this sort of thing and say, oh, it's like a coin flipping thing. That would probably confuse the heck out of something. It's one interpretation. It kind of works for the setup of this thing when you're thinking about all of this. But if I were going back and interpreting these things right here and interpreting the distribution, I would say it's the Poisson forecasting distribution. And I would explain it in the context that I derived it. And so if I tried to make any connections with like a scientist or an engineer and it wasn't classroom time, they'd probably just be like, what are you talking about? So, because it doesn't really relate to the problem at hand, unless they were counting coin flips in the first place. So if they were flipping coins and they were counting how many, something like that, and they were flipping coins and they were looking for certain counts, they're modeling things by Poisson. I guess you would do that because N is big and P is small, so you use that approximation. Maybe you can carry over that interpretation, but I wouldn't. So that's why I like the iterated forms for this one, because then I don't have to think about any interpretation other than what it actually is. It's a forecast for what Poisson. Good question. Let's do some other stuff. So let's not do math for a little bit. So let's just answer some questions. You might have some questions circulating about estimators that you might get from posterior distributions. One such estimator that you could pluck off, the Bayesian in a lot of ways gives you too much of an answer. They give you the full distribution. Now, if I were programming a robot or something like that, I would use all that information. It's just a mathematical equation to me. If I were forecasting, I'd want the entire uncertainty of the posterior distribution. But when we're doing science or engineering and we're trying to understand things as humans, we need to simplify things quite a bit. So we don't even understand tail behavior very well. And so very commonly, we like to give people a point estimator, and we like to give people an interval. And so we've talked about the expectation. There's another estimator that's very common, and that's the mode. So the mode of a posterior. So this is the tallest point. It's called a map. And it stands for maximum A-Posteriori estimator, if you like. Max A-Posteriori. I say map all the time, but it probably would have been easier to just call it the max of the posterior. And so you have a question on your homework. We talked about it briefly last time. Do they share the same invariance properties as MLEs? And sometimes they do, and sometimes they don't. And that's what that homework question is. So if you want to be in good shape with that homework question, you'll figure out in which case are maps invariant to transformation. Does anybody know the answer off the top of their head?
Linear transform.
Very good. So that's it. So the camera is really close to Rujan, so you will hear him. It's a linear function. Linear transforms, maps are preserved. So you can work through that. If you want to sketch of a proof, there's already a statement about MLAs being preserved. Posterior distributions are products of priors and likelihoods. So the likelihood part is invariant to transform. It's when is the prior invariant to transform. It's really when is the Jacobian or the derivative function a constant. It doesn't have the parameter in there to move things around. In general, maximums of functions are not preserved. So likelihoods are kind of interesting because likelihoods don't have the derivative in them. It's just a function. It's not a probability. You're not allowed to integrate over it until you turn it into a random variable. And so, let me just show you real quickly. So maps in general, or I'll just say modes of this. It doesn't matter that it's a posterior. There was nothing fancy about it being a posterior distribution. So modes of distributions, and I'll say continuous. Discrete distributions don't have the derivative either. And that's the part that you need to make sure doesn't move your space all over the place. But modes of distributions are not necessarily invariant two transforms. We talked about this for a minute when we were discussing the homework last time. So what does that even mean? So invariant to transform, what are you talking about? What's invariant? So what they mean when they say this, so I'll just tell you, maximum likelihood estimators are invariant to transforms. It doesn't matter which transform you use. It can be non-one-to-one, it still works. So for MLEs, max likelihood functions, if you start integrating over your likelihood functions, you treat it, the thing as a random variable, I'm going to call you a Bayesian. So I'm going to say, and you just don't know anything about priors or what you just did. You either did something really good or something really bad. So I have seen people start integrating over likelihoods. Probably the pestiest thing you can do to them is accuse them of being a Bayesian. For some reason, they don't like to say it. So anyway, that might be going away these days. So for maximum likelihood estimators, I'll say you have some distribution, xi's are coming from this. Doesn't even need to be IID or anything like that. If the likelihood function looks like this, so I'll call it this thing, same notation that we've been using, and it looks like that. That's the MLE. This is the MLE, I should say. Theta hat MLE, that's the point that maximizes that function. That's the max of the function. This thing right here is the argument that maximizes the likelihood. And I don't need to undermine this. This can be a hard problem. So figuring out where the maximum of a function is if you didn't know anything about it. In 1D it's easy, and in high D it's hard. So for all the reasons that we maybe discussed in calculus class with you, or because of sparsity. You have to search all over the space. In a one-dimensional, probably you can just sweep and do a pretty clumsy algorithm, probably find your max pretty quickly. You could do bisection searches or golden ratio searches if you wanted to speed things up a little bit. So you can do other things that are even faster. Whole fields are built around trying to maximize functions. And different types of maximizers or optimizers work in different classes of functions. So in general, this could be a hard problem. If you're interested in transforming, so say you wanted to know about G theta, some transformations. So if you're thinking about variances, you might switch over to sigma, the standard deviation. Or you can put things on a precision scale or something like that. So a lot of different transformations. They mean exactly the same thing, but they just help us to interpret things in different fields a little bit differently. And so you wanted to know about this, then G theta hat MLE, that answer right there is the maximizer. This is what people say. People will say that the MLE is invariant to transforms because of this. Question. So distributions don't share this property. So distributions, continuous distributions, in general they don't. But it does depend on the type of transform, and we already have our answer for linear functions. Bayesians are in good shape, and where you would want to think about is the derivative of everything. We won't do a review session tomorrow, but we will do one next week. So if I'm confusing you, you can ask me about it, and I'll help you think about that next week. Okay, if you want to look it up, any inference book, grad level inference book, Casella and Berger, for instance, will have the invariance of the MLE property. You can even go to the appendix or the index, and it'll tell you where to look it up. So just look up the word invariance in Casella and Berger, or look up the MLE or something like that, and it'll show up immediately. the index. Okay. So modes of distributions are not necessarily invariant to transforms. Here's an example of that. This would suffice as a counterexample for your homework, but it's not very informative. It doesn't tell you why it's happening. So a real proof might help you to understand this. But say I had a posterior, any distribution, let's say it's a normal. So I'll say Z is equal to a normal 0, 1. Let's say you collected data and for some reason your posterior was normal 0, 1. It's just an example. We'd never happen. So, but let's say you're working with that. Let's say you standardized everything and everything was conjugate, it lived normal, and you can make it a normal 0, 1 on some scale. If I wanted to think about this transformation, I could work through some math and figure out where the maximum is. Where's the max of this? So the max is at 0. We know what that distribution looks like. That was right there. Z squared, what's this distribution? It's chi squared. With 1 degree of freedom, its maximum is 1. It's the degree of freedom. So if you didn't know that, chi-squared distributions, their maximums are the degree of freedom. So another easy thing to remember. I'll never ask you to, you don't need to know that for this class, but it's true. So this right here is not 0 squared. So if this was true, if the maximums were invariant, then I could square that and get that one, but it's not true. And what's going on? It's the derivative term that messes everything up. So if the derivative were a constant, it would preserve everything. Something for you to think about. Let me ask another question. Say we have a bivariate problem. Say we know the max, and I'll say the argmax over 2 parameters. So I'm going to imagine some posterior distribution with 2 parameters in there. Again, there's nothing inherent about this being a posterior. It's just that all Bayesians do inference off of an actual probability distribution. I'll distinguish that from what a classicist does. We do not do that. Think about a p-value. P-value is conditioning on a null hypothesis and thinking about more extreme data or something like that. And then making a conjecture about what they've conditioned on. So they didn't cut theta on a probability space. Bayesians always do that. So let's say I know what this is right here. Theta 1, theta 2 max. Here's my question. Say I have these 2 distributions. So I'll say pi theta 1 given x is equal to the integral. Say I was able to do this. I integrated over theta 2. I'm integrating that whole thing out right there. And say I had, similarly, the margin for theta 2. So I had the margins. If I maximize these things, arg max theta 1 on theta 1's margin and arg max theta 2 on theta 2's margin. Now I'm just going to call this theta 1 tilde theta 2 tilt. So my question is theta 1 hat equal to theta 1 tilt? And similarly, is theta 2 hat equal to theta 2 tilt? So can I take a high dimensional, 2 dimensions in this case, maximization problem, and turn it into a couple marginal maximization problems? What do you think? The only reason I bring up these questions, even the thing with invariance of maps, is I've seen it in lectures before, or in talks, where somebody's like, oh, I just took my map and I transformed it. And it's like, can't do that. So that's not the same answer. Hopefully it can change your whole conclusions to everything. So I hope they might be in the ballpark of each other. I've also seen this done, where people are like, they take the margins, they maximize them, and then they say, well, that's the joint max. It's not true. So let me show you a picture. I created a quick example. I wrote a piece of code that does this. I'll show you that code maybe when we come back next time, but it really just plots some stuff for me. So I made that plot, that distribution. So I'm calling that some distribution. You can think about this as a posterior distribution. You could think about it as any other distribution. There's nothing special about being a Bayesian that this happens. It's just that for probability distributions, the margins don't preserve the modes. So here's what my distribution looks like. That'd be pretty funky. If I got that, I'd be really excited. If that was like a real science problem. Wow, what is going on? There's some weird confounding in here. So, does anybody know how I made that? That's 3 normal distributions that are superimposed on each other. So when I've normalized it so it would integrate to 1. So I put some amount of probability weight on this distribution right here. That looks like just a round normal distribution. And then I took some other normal distributions and I built a lot of covariance into them. And so it overlaid them into each other just so it looks really interesting. Can you see what would happen if I marginalize over this distribution? So if I had it like this, I made these things right here, these ridges, or whatever you'd call these. I don't know what you call these. So these beams, buttresses, any civil engineers? So something like that. Gussets? Is that a problem? No. So I just did on axis parallel. So when we started to average things, so if I start to add in this direction, if I add in that direction or I add in that direction, things happen the same way because of symmetry, but this is different in these 2 directions, which way I marginalize. So I marginalized that distribution, and this is what the margins look like. So that's the little peak that's sitting off by itself. So that was centered at minus 10, 10. If you go back to that figure, you'll see it's centered at minus 10, 10. So that's where that is, right here. And this thing's centered at 0, 0. And that's where these are. So these are my 2 marginalized distributions. How did I do those? I put everything on a grid, and I just added it up in the 2 different directions. And then I connected the lines so it looks like a continuum. So as I'm adding more and more, it could bring up that mode right there. And so if you were trying to report something jointly, I'd be really interested probably in both points to ask what's really going on. So that's just a misconception that sometimes people have. Very easy to work with margins of things, but be careful, it's the joint relationship that really matters. Okay, we'll come back next time and talk about credible intervals. So I'll tell you conceptually about credible intervals. We've already seen an example where the credible interval and the confidence interval are the same things. We've seen examples where they're different. So in your binomial homework, you got different answers for their coverage rates. If you're using a normal distribution and you're building a 95% credible interval versus a confidence interval, the Bayesian and the non-Bayesian would probably report the same things. So if you're using a flat primary, you would report the same thing. I want to dwell on that a little bit more and show you some examples where the Bayesian and the non-Bayesian totally disagree with each other on the interpretation of those variables. So we'll pick up next time with that. Thanks, you guys. And also, don't forget, we have Friday off.